or two comments on the whole development of ideas I conveyed in the last 2 hours. I proved almost no theorem. And I can tell you, to prepare the lecture this way is much more difficult than just make theorems and proofs. And if you had a look at those lectures I have sent you by email, you will see also that some quite great mathematicians apologize every time with his students if he makes a proof. He apologizes. But it's a bit exaggerated. But of course he has a book. But I think even if there is no book, you should still teach not deductively, but inductively. First comes induction, and then comes, of course, the proof, which is deductive. Okay, but there must be this one, not only this. Well, I come back now to one other remark of myself at the end of the first hour. This remark was made on the example of fitting the line and the matrix G being equal to x1 to xn, 1, 1. And then we said, well, if those x's are too close to each other, then maybe we have made a wrong choice. And then look, the other dependence. Completely analogous, same formulas. But then, well, that means, in a sense, to take this coordinate system and rotate for 90 degrees. A purely mathematical, geometric question would be, why rotate for 90 degrees? Why rotate any angle, which maybe would be better? In other words, let the method choose its own coordinate system itself, and not we. It's easy if you do it with just a line, but if you have thousands of variables, then you have no insight. And letting the method do this choice may be a good decision. So what does it mean? Let the method make its choice. What does it mean? That means that we are sort of pose a question independently of the coordinates. So we have points here, and we try to put a line. What's the best thing to do? Instead of choosing coordinate system as we did and making differences as we did, forget about coordinate system and measure what? Measure the distances of those points to the line. This is independent on the coordinate system, obviously. And then try to make some good optimization of it. In the sense L1, L2, L infinity, whatever. I think I have some some picture here which I can show you what I mean by that. Okay. Exit. I would like again to come to my too much icons. Computer, where is the computer?
Yeah.
Computer. File manager, yeah. Okay. My stick. Okay, yes, very good. 21 GIFs, course GIFs. Okay, very good.
Oh,
yes, okay. So, you see, now we rotate a line and look at the distances of the various points to this line. Here, the point of rotation is fixed. In general, we also have to optimize over all such points. But somehow it seems natural that those point around which we are rotating must be somewhere in the middle. That's clear from the picture. And you see that this would be about the best position. Here. Now let's put this geometry into formulas. I don't know whether one learns such things in the first course on linear algebra. That's the distance between a point and a line. If a line is given as ax plus by plus c equals to 0, you see now the formula treats equally x and y. So what's the distance? The square of the distance is equal to ax di, ith point, plus v y I plus c square over a square plus b square. That's the formula for the distance, for the square of the distance. Of course, the denominator should be positive, and that's natural, because if both a and b are equal to 0, there is no line. So what we have to minimize is the following. Sum I 1 to n vi square is equal to sum I 1 to n a x I plus t y I plus c square over s square plus b square. So now the variable over which it is quite easy to optimize is c, because it comes linearly. So if I call this d, then d is equal to 1 over a square plus b square sum r1 to the n a xy plus b y yi square plus n c square plus 2c over n sum y equal to n a xi plus b yi plus minus 1 over n square sum y1 to capital N a xi plus b yi square one two so it's correct. Yes. Just square this. This plus this square. So now this is equal to 1 over a square plus b square times c plus 1 over n sum I1 to n a xi plus b yi square plus sum I is equal to 1 to n a xi plus b yi square minus 1 over n sum 1 over n a xy plus b yi sum squared. Now this is known to be greater or equal to 0 by the Schwarz inequality. Anyhow, and anyhow it's constant with respect to c. So we can minimize this. How? Well, by taking this to be 0. That's easy. The optimal c is equal to minus 1 over n sum a xy plus b yi, which can be written down as minus a x bar minus b y bar, where x bar and r bar are just mean values. And so on. That's what this picture was showing you. It was rotating the line around the mean value of those points, which is anyhow the best, independently of what the others has to say. So my D now reads as follows. Sum I, or 1 to the n, a psi I plus b eta I square over a square plus b square. Well, eta I is yi minus y bar, and xi is xy minus x bar. I mean, I put the the origin of the coordinate systems in the center of gravity. Of course, I didn't tell you that in everything which is written here, you also may have weights. Nothing would change, essentially. So that's what has to be minimized. This is, by definition, non-negative. By definition. So let me compute this. This is times 1 over, okay. It's equal to 1 over a squared plus b squared, a squared, sum I 1 to n psi I squared plus 2ab sum I psi I eta I plus b squared sum I eta I squared. It's a symmetric function. And this now can be written in matrix vector form as A transport capital A over A bold, this is bold faces T A, where bold A is equal to A and B, and A matrix is equal to sum I Ci square sum I Ci eta I sum I Ci eta I sum I eta I squared. Well, this is a symmetric matrix, and it's positive definite by definition. You can prove its positive definiteness directly from this formula if you wish so, but you don't need. The proof goes just back to this formula. That's the proof why such a matrix is positive semi-definite. It made to make your computation backwards and get this sum of squares. Now, so we are left with the following problem. Find out minimum over the vectors A, which of course are different from 0, of this expression. I know it's annoying to remind the students to recall something which was on the board for several weeks, because usually one forgets everything. But we had a formula which could help to solve this already. And this was the so-called minimax formula. If we have any symmetric matrix, real symmetric matrix, which we may call A in general. Then we know the following. A equals to A transpose real. And then if we denote the eigenvalues of it by mu1 less or equal to mu2 and so on, then mu k is equal by, as a formula, max min of xt ax over xt x. Well, over what? This goes over x from Sn minus k plus 1, and maximum goes over Sn minus k plus 1, where S is a subspace of a given dimension. So you fix the subspace, minimize these over the fixed subspace, and then maximize over all of them. And then again, you can do it the other way around. Minimum sk, maximum over x from sk of the same expression. So now what would be mu1? In mu1 you have a one-dimensional space, so this is way. So it is just mu1 is just minimum of xt and xt. So this expression, when you minimize it, you get the lowest eigenvalue of the matrix A. And that's what we need here. So this will be the lowest eigenvalue, I mean the lower, because there are only two in this case. mu1 of A, the lower eigenvalue of A. And the vector is the eigenvector of this belonging to this eigenvalue. This eigenvector is uniquely defined up to the direction if the eigenvalues are separated. If they are multiple, then you have a much greater freedom in eigenvectors. But if they are separated, then the direction is uniquely defined. And that's what we need. So what we get here, we get an A and B and what does the vector AB for the A psi plus B eta is equal to 0. In new coordinates there is no C. Well, that's just the orthogonal. So the vector AB you get from this is just the orthogonal to the best plane, to the best line. Orthogonal. But these are the points. So the method indeed choose a best direction for that themselves. What this direction is? Well, this is the solution of the eigenvalue problem of this particular matrix A, which is built up from the coordinates of the points we have to approximate. No, the same things happen in many dimensions. I will just repeat with some springing of similar formula the case for the arbitrary dimension. We have points xy is equal to xi1, xin. I is equal to 1 to capital N. You have n coordinates and capital N vectors. And capital N is always much larger than the small n. So to minimize is again sum of the distances square which are equal to sum or I A1 x I1 an x I n minus c square over a1 square plus an square, which can be written in the matrix form as sum I a bold transpose xi plus c over a bold transpose a, where a bold is equal to a1 to an. Again, minimizing over C, just as we did above, gives optimal C as minus A transpose X bar, where X bar is equal to 1 over n sum I 1 over capital N psi I. So we have to minimize then again this expression, which is equal now to sum at psi I square over a square 1. And then again squaring this all, you get this as again expression ATA A over a square. Well, Aij is the matrix obtained as a sum 1 over capital N to capital N psi chi ki psi kz, which is again symmetric at positive semi-definite. Well, when this matrix will be 2 semi-definite, that means singular. Well, when this expression is 0 for some value of a, and that's then when all xi's lie on the manifold, which is defined by the equation Now, what we would call now the significant correlation, significantly, well, if the lowest eigenvalue, and that's the lowest distance, is well separated from the next one. It's intuitive. Just numerically, if two eigenvalues are quite close, then the eigen vectors are separated, but not badly. That this separation is then susceptible to round errors, and these are big. So you should have distant eigenvalues. But that's not the end of the story. What about the other eigenvalues of A? Do they have some meaning? Only assuming that they are well separated from each other. So that's, I think, the last thing I have to do. It will take some 5 or 10 minutes. I think we can struggle with that. So let U1 be the eigenvector of A for the eigenvalue U1. Smallest eigenvalue. Then, as we said, U1 is orthogonal to the best hyperplane, this one. We take A being U1. We choose so. That's the best plane. Now, we introduce now new coordinates. We now choose the coordinate system such that the first coordinate has a direction of U1. This problem will not be affected by that. Choosing orthogonal coordinates means orthogonal transformation. So eigenvalues do not change by that, nothing changes. And to see that that's true, let's now introduce right psi being equal to Q eta. Q, this matrix Q is connection between two orthogonal systems. That means it's an orthogonal matrix. And we choose it such that Qt U1 is equal to the first canonical unit vector. There are plenty of such transformations, but certainly at least one which maps two given unit vectors into each other. You may choose any such matrix. So now, this sum here is equal to sum over I bt eta I square over btb. Well, A is equal to QB and C is equal to Q eta. It's simple transformation. You see that BTB and ATA are the same. These are the norms which don't change by the orthogonal transformation. So now the new matrix B is now equal by sum k eta k I eta k j. And forgot to write down the following. Excuse me. This is dt dB or dTB. That's the line I forgot to write down. And this is, if you connect those two, and this is then QTAQ Rj. This is just your B. So B is equal to QTAQ, or the same as Q2 minus 1 A2. So this is a similarity transformation. The eigenvalues do not change. But more, we know more. What about B? What does B if acting on E1? This is QT AQ on E1. And QE1 is U1. So this is QT A U1, and that's the eigenvector of A. So it is it's mu1 QT U1, and that's E1. It's mu1 E1. So this is the matrix B acting on the first canonical vector gives just something which is proportional to it. So its first column has mu1 on the first place, that zeros down there. And by symmetry, the same is with the row. So, or B looks as follows. mu1, 0, 0, and here is some B2. Again symmetric, again positive, semi-definite, and so on. So now, what's B2? Ij in new coordinates. You see, I'm using these now. These are the sums. K equal to 1 to n, just the same thing as up there. But now I and j go from 2 to n. So what are those coordinates? These are just the components of our points to the hyperplane orthogonal to A. So what this all boils down to, let's look at the plane. We have points, and we found a best plane. So now we are looking for the projections of those points in the plane. And now approximating by the next smallest dimension. In this case, that would be the line. And so on. How far would you do that? Well, as long as the eigenvalues are well separated. Once they become undistinguishable, then the rest is rubbish. As a good exercise showing what happens in the rubbish case, try to find a set of points, say in the three-dimensional space. such that the resulting matrix A is scalar, has all eigenvalues equal. That means rubbish. Try to find the simplest configuration of points, 4 or 5, 10, such that the matrix A is scalar. That will teach you the best way what you should avoid and which situations have no information in them. So you see, in many cases, the eigenvalue decomposition is working like a magnifying lens. We use it, that term, in some other context. But magnifying lens giving a deeper insight both in the frequencies of a vibrating system, or else in the solving classical least square problem. What's the difference? There we have also some eigenvalues, singular values, and here also somewhere. The difference is that here we also take best coordinates. We don't prescribe who is the function of whom. That may be sometimes needed. So here again, you have a situation where a couple of parameters can well describe the whole bunch of data in the best way you can hope for. For example, you have let's take the first eigenvector u1, which has some components u11 to u1n, which is equal to sum u r1j over ej. Ej are canonical unit vectors. What this eigenvector tells us, it gives us, if the coordinates 1 to n gives some data on persons, their age, their height, their weight, and if you get a significant mu1 small enough, then those components will give you which of those quantities come together that are correlated. And this is again a case of dimension reduction in a sense. Dimension reduction is a matter on which you can keep held of quite a lot of lectures. And the whole Google business has to do with that. To extract important characterizations of the data you wish to have. So, well, I think that's now point to finish this short overview of least squares. I hope I wasn't being annoying you with things which you know sometimes much better than myself from your studies, but it was my hope that you will get some better overview. So next time we will meet on Tuesday, and we will have the lecture from 9 to 11, and this will be now consecrated to quite a different topic, namely the computing tomography. It will be simple geometry, no forces, no potential energy, nothing, just geometry. forget that the geometry is the basis of mathematics. The people who have no geometric view are much poorly equipped for doing this.